In the last lecture, we introduced the concept of even and odd permutations. A permutation was called even if you could write it as a product of an even number of transpositions, and odd if you could write it as a product of an odd number of transpositions. And we saw that a lot of the things we did in that lecture actually didn't make sense unless we knew that every permutation was odd or even, but not both. In this video, we're going to explore exactly why that's true. We'll just do a very sketchy outline of why it is. If you'd like to see some more details, you can find them in the online notes. So I want to begin with an observation about transpositions, which is that every transposition is its own inverse. So if you have a transposition, and remember that just means a two-cycle ij like this, where I is not equal to j, and if you compose it with itself, well, this permutation ij swaps I and j. So if you swap I and j twice, you're back to where you started. Therefore, their composition is the identity. So ij to the minus 1 is equal to j is equal to ij. Okay, so here's the statement of the odd and even theorem. All it says is that no permutation is both odd and even. And let's suppose for a contradiction that it's false. So if we suppose that we have a product of an odd number of transpositions equal to a product of an even number of transpositions, let's say t1 up to t2l plus 1 is equal to s1 up to s2k, where si and tj are all transpositions, or two cycles in other words. Well then, what we can get from that is that if this were true, then you could write the identity as a product of an odd number of transpositions. The reason for that is you could take this equation and multiply on the right by the inverse of s2k. But the inverse of s2k is s2k again, as we just saw. So we get s1 up to s2k minus 1, and we could keep doing this. So if we keep doing this with all of the s's, we get t1 down to t2l plus 1 times s2k minus 1 down to s1 is equal to the identity. So here we've written the identity as a product of an odd number of transpositions. It's enough to prove then that this is impossible, that it's impossible to write the identity permutation as a product of an odd number of transpositions, and that's how our proof goes. The next concept we need is that of an adjacent transposition. An adjacent transposition is one of the form I plus 1 for some number I. So why are these things useful? Well, the reason is their action on a certain object which we're about to meet is rather easy to understand, and it's a fact that every permutation can be written as a product of adjacent transpositions. In fact, even better than this, every transposition can be written as a product of an odd number of adjacent transpositions. And let's see why this is. So we're going to begin by drawing a diagram for a transposition. So here's an example diagram for a transposition. Here are the inputs. And there are the outputs. And let's say I want to swap position 1 and position 4. So I'm going to have a diagram that goes like this, and a diagram that goes like this, and they meet in the middle. And then we'll form the rest by having a mirror image like this. So we'll reflect what we draw on the left in a mirror. Now, why is that useful? Why is this mirror useful? Well, the fact that we can do this with a mirror tells us that the number of crossings, so the number of times these lines cross, is odd, because you've got a crossing in the middle here where the mirror actually is, and then every crossing on the left is reflected to another crossing on the right, so they pair up. Every crossing on the left is paired with a crossing on the right. But each crossing corresponds to an adjacent transposition in such a way that when you compose all the adjacent transpositions, you get the permutation whose diagram this is. To see what's going on there, let's draw a much larger diagram at the bottom here. It really is going to be a big diagram. What do I want to do? I want to swap over this thing and this thing. So there's the crossing in the middle. Let's have different colours for the other ones. So this one, well, let's see what happens. We're going to cross this one here, and then it's going to cross this one again on the other side, and the other one is going to cross this one just here, and it'll cross this one on the other side like this. Okay, well, now to see what I mean about adjacent transpositions whose composition is the transposition whose diagram we've drawn, let's just put in some extra blue dots here. So I'm going to draw in some extra blue dots so that there's only one crossing between each set of blue dots. So the whole permutation here was just the transposition 1, 4. And what the diagram shows you is that this thing 1, 4 is equal to a composition where we take one, 2, so this is, here is 1, 2, and then 3, 4, and this here is 3, 4, and then this here is 2, 3, then the next one is 3, 4, and then the last one is 1, 2 again. So this kind of diagram allows us to express any transposition as a product of an odd number of adjacent transpositions. Okay, so what the diagram suggests is that every transposition can be written as a product of an odd number of adjacent transpositions. And it's not too hard to make this into a proof. You can see an actual explicit expression for a general transposition as a product of an odd number of adjacent transpositions in the odd 9 notes. Alright, so moving on, what's the next step of our proof? The next step is where it gets really interesting. So we're going to think about our permutation in Sn, and we're going to introduce some variables. We're going to let x1 up to xn be variables, the kind of variables you might form a polynomial out of, like x squared plus xy plus y times z. But we're going to call our variables x1 up to xn. Now if we have a permutation f of the set 1 up to n, and if p is a polynomial in the variables xn, then we can define a new polynomial. So f of p to be the polynomial you get by permuting the variables, by letting f permute the numbers of the variables. So that is f of p is p of x, f of 1, x, f of 2, and so on. So as an example, if p of x1, x2, x3 is the polynomial x1 squared plus x2, x3, and if f is equal to the 3 cycle 1, 2, 3, then f of p is another polynomial in those variables, so it's p of x. Well, instead of x1 I have to put x2, and instead of x2 I have to put x3, and instead of x3 I have to put x1. So what is that? We take the first variable and square it, x2 squared, and then we take the product of the remaining two variables, so x3, x1, like this. So for each polynomial p and each permutation f, we get a new polynomial f of p, like this. Now we're going to define a special polynomial, which I will write like this. So define delta n to be, it's going to be defined to be a product. So if you haven't seen the symbol before, then all it means is just like the sigma symbol for sums. Well, this capital pi is just like that, only for products. So we multiply together all the things I'm about to write down. So it's the product over all I and j between 1 and n, such that I is less than j, of the polynomial xi minus xj. So for example, delta 2 would be just a single factor x1 minus x2, and delta 3 would be the product of all factors xi minus xj, where I is less than j and I and j are between 1 and 3. So we have x1 minus x2, and we have x1 minus x3, and we have x2 minus x3, and that's it. Those are the only factors there. So these are some polynomials in these variables x1 up to xn. So let's finally start thinking about what our permutations do to these delta things. So let's notice first of all that if you take the identity and you do it to delta n, then you get delta n again. The identity doesn't do anything, of course. But now let's see what happens when we do an adjacent transposition to one of these delta n things. So let's say if we have any adjacent transposition, let's say r plus 1 of delta n, well, I claim that is minus delta n. So the reason for that is if you do r plus 1 to any of the factors in that polynomial, so xi minus xj, it still has the variables in the correct order. So what is it? It's x r of I. What is it? Let's write this a little bit more carefully. X subscript r plus 1 evaluated at I minus x r plus 1 evaluated at j. The only way this can be the wrong way round, in the sense that the variable on the left had a bigger index than the variable on the right, So it's one of the defining factors in delta n, unless I is r and j is r plus 1. So there's only one factor in delta n which has its sign flipped when you apply an adjacent transposition. Conclusion: a product of an odd number of adjacent transpositions will send delta n to minus delta n. But the identity sends delta n to delta n. So that means the identity cannot be a product of an odd number of adjacent transpositions, and we've finished our theorem. Now you might wonder, why did I bother introducing these adjacent transpositions? They're not strictly necessary in this proof. You could, if you wanted, just carefully analyse the effect of any old transposition, not just an adjacent transposition, but any transposition on this polynomial delta n. It's a little bit harder, but you can do it, and you can show that any transposition sends delta n to minus delta n. But the advantage of doing this with adjacent transpositions is much more obvious what effect an adjacent transposition has on one of these polynomials delta n.